Hello everyone, I would like to finish up here on the last little bit of information that's in 2.7 about these functions and also the piecewise functions, different stuff like that. We're talking about this time this idea of increasing, decreasing, and constant kinds of behaviors that we can find in graphs of functions. And then we're going to move on, talk about the next one about minima and maxima, stuff like that. And so at the beginning, I just want to make clear that for the purposes of this course, we're not going to get really into the nitty-gritty of this one about why this should be the case. I would like to explain why, and I will try my best while staying in the bounds of this course. But when we're talking about increasing, decreasing, and constant functions, these ones actually are notions from calculus where we're interested in basically this idea of a derivative, which a derivative is basically something about the slope, which whenever we're talking about the slope of a curvy line rather than the slope of a straight line, it gets a little bit more complicated. But we basically come up with these notions of increasing, decreasing, and constant based on what the derivative is. And here, derivatives are actually only defined on open intervals. It is not possible really to define a derivative only at one single point, and so that's why we don't want to include the endpoints of intervals. Open interval looks like this, for example, from A to B, using the parentheses. This one makes it open, whereas if we put the square brackets over here, it would become closed. And so we will define our increasing, decreasing, and constant intervals always using the parentheses. And it seems kind of weird that we should do that necessarily, especially for the one about constant function, like why should it matter if you include the endpoint or not? And the simple answer is that it is a convention for us at this point that we're going to use the definitions that exist elsewhere, that so you don't get a definition now and then when you take calculus you get some other definition or something like that. We want to keep it as consistent as possible, so always this kind of interval what it's talking about, this one should be open interval. And we will just move on from there. We could talk about a little bit more stuff having to do with that, I would like to, but we want to see maybe just how we can identify the increasing, decreasing, and constant intervals for one of these problems. And really, we can talk about, just for the example 12, what I mean about why we should use open one, is that for something to be increasing, which here we want to talk about the increasing intervals, and you can see that basically it's increasing along here from, basically from negative infinity over there, we can see that that's where it starts increasing. At least the graph gives us that impression. And then it should stop increasing by the time you get over here to -2. That's when it becomes constant at that point. But whether we should include 2 or not, you know, if we want to say that it's increasing actually at the point of 2, then we would include the point 2, but that's what I want to talk about. What if we do it this one? We say it's increasing like this. What that means is that we should say it's increasing at the point 2, but then the way that we should know that it's increasing there is that if we look at a point after 2, the point that's after 2 should be higher. Like we should say that f of, based on this definition that we had over here, f of 2 should be less than whatever goes here, f of a or something. This should be something to the right of 2. And then we can also say that f of 2 should be more than something that's to the left, like f of 1.9 or something. We should be able to look on both sides of 2 and say that it's basically increasing from the left, and it continues to increase as you go to the right. But here, with using this closed interval, like using the square bracket, it's not possible anymore to pick something after 2. If we do it this way, the correct way, which we will use parentheses, then we're not allowed to pick 2 actually as the point where we say it's increasing. We say it's increasing all the way up to 2, just not including it. So then no matter which point you pick, you can still always pick something to the left of that point. You can pick something to the right of that point that's also still less than 2. So it's not a problem. Like you could pick, you can say f of 1.9 is less than, we need to pick something that's more but still less than 2, like maybe f of 1.99. But then we can still pick something that's to the right of that one, like 1.999. It's still less than 2, but now it's to the right of this one. And so it works out for us. And any point that you pick, like there's always, numbers after this that are still, after 1.999 that are still less than 2. There's as many of them as you want to pick. You just add 9s until you cannot add 9s anymore, which you can always keep adding 9s. So you can add like infinitely many of them. And so we have increasing there. And then you notice it starts increasing again at 2. And then it just keeps going forever. So it's increasing all the way, just keeps going to the right all the way infinitely in that direction. And then we notice that it's decreasing somewhere over here. It starts decreasing by the time it gets to 0 up until 2. And so we would say from 0 to 2 it's decreasing, but we don't want to include the endpoints because of the reasons we mentioned. And then the constant one, it's constant all the way from -2 there up until 0. That's where it's not increasing or decreasing. It's from -2 to 0. So we will have that one. And that's very good. We will look now at this idea of basically the minima and maxima for a function. And this one, we are still kind of having a little bit of a notion here talking about basically these open intervals, but open interval here, it's not as important necessarily to be talking about that one. That's mostly for increasing or decreasing. Here, it's very important to notice that we're talking about this idea of relative. This is in contrast to the idea of having an absolute one. There also exists something like absolute. Absolute. We will call these extrema. Extrema, like plural of extremum, which is a minimum, maximum. Those are extremum because those are extreme values. The absolute one is for the whole graph, or else for the whole function. I'll just say for the whole graph because here we're mostly focusing on this idea of graphs, but for the whole graph or function. That's what it means absolute. It means out of everything it's the maximum, or out of the whole function it's the minimum, whatever the case. Here when we're talking about the relative one, the relative extrema, this one is only for basically for small little intervals, for small or else tiny, for small chunks, as it were. It's not very technical to use these kind of words like small chunks, or else I like to use this word neighborhoods. For small neighborhoods of points. And that's what it means relative. It means related to the points that are just right around that one. And so you can see on this graph that it's showing us, for an example, this kind of a curvy one. It's showing that even though this is not the highest point, this f of a, because the function attains higher values over here, all of these kinds of values are higher, it's a relative maximum because if you only look at this value, this x value of a, and you only look right around there, and you're not looking anywhere else on the function, only right at that point, you can see that it is higher than any of the points that are close to it. And that's what makes it be a relative maximum. Same deal for relative minimum. It is lower, it is a smaller y value than any of the other points that are around it. And you can make this interval that you're looking at as small as possible. That's actually the idea for doing the relative one, is that you want to consider, well, what if I'm looking super duper close to this point and only looking at the points that are extremely close to it? Is it still the smallest one? And so that's what we're dealing with here. Now let's see for number 14, the location of the relative maxima or minima. And here, by the way, these maxima and minima, these are always y values. and you say that the maximum or the minimum is that y value, and you say where it occurs. It occurs at an x value. And so that's what we have here, like at x equals something. At x equals something, the function has a relative minimum of something else. Then that's where the y value goes, is here. And so when we're looking at this, when we're looking for the minimum, and you can see that around here, and you're basically looking for these kinds of like a valley kind of thing. Like the relative minimum is this kind of a valley shape. Relative maximum is this kind of like a hilltop shape like this one. And here, even though it's pointy, there's a bit of a valley shape over here at the bottom of this point. And that value, you see the point, this point of, should say -2, 1, it's the lowest point out of all of these other points that are around it. You know, if you zoom way into that one, and why don't we actually do it? If you just zoom way super close into this one, you can see that that point that is just there is the lowest point out of all the ones around it. So no matter how small of an interval you look at, you just look very close to -2. We're only looking, you know, in between here, it is the smallest point. Because if you zoom in on that shape, it's this V shape, we're getting the bottom of the V. So that's the point of that one. Now, that means that in that interval, and of course we're surrounding, trying to get the right amount of zoom here, we are surrounding x equals -2, and that point, it's the lowest point in a very small interval or very small neighborhood surrounding x equals -2. And so what we would say is at x equals -2, the function has a relative minimum of -1. Oh, and this should have been negative, I'm sorry for that one. It's the point -2, -1, of course. And then what about this one talking about the highest points? You notice there is a highest point, a kind of a hilltop there. At this point that goes like 0, 1. If you zoom in very close to this one, you're seeing that 0, 1, it's the highest point, it's kind of the top of a hill there. No matter how much you zoom in, you will not find another point around it that's higher. And so in a small interval surrounding 0, 0, 1, it is the highest point of all. And so we would say at x equals 0, the interval has a relative maximum of 1. And that's really all there is to it. It's not too big of a deal. If you guys have any questions, please let me know, but I hope that this video was helpful for you all. And we will pick up a bit later in some other sections where we still have a bit more to do in chapter 2, but we will get it done. So thank you guys. Thanks for watching.